The purpose of this video and code file is to demonstrate that regression and ANOVA are exactly the same thing. It's a question I commonly get in statistical consulting. Should I run an ANOVA or a regression? And the answer is that you can do one or the other. They're exactly the same model. I like to think of ANOVA as a way of formatting the output from a regression, but I suppose you could also say that the traditional regression output is just a way of formatting the output from an ANOVA. Either way, they're the same model, but the defaults, the conventions associated with ANOVA and the defaults or conventions associated with regression are just different. There's different choices of tests that are shown with each of these. So what I'm going to do here is use a particular built-in data set in a particular R package to try to convince you that this is true, that ANOVA and regression are actually running the same model, but there are just different defaults in terms of the p-values tests that are displayed. The data set that I'm going to use is called mSleep, and it's a data set that's built into the R package ggplot2. This is not a tutorial about ggplot2. You don't have to know how to use ggplot2 at all to be able to use the data set. All you have to do is open the package. So in my R console right now, I have already installed the package on my computer, but I'm going to go ahead and run the line for the library ggplot, which means that I now have the mSleep data set available to me. So for example, I can look at it, let me make this window a little bit smaller, I can look at it and see that the number of dimensions are 83 rows and 11 columns. And if I want to, I can look at the first 6 rows, and this gives me a better sense of what's in this data set. You can see there's some animals in here. So I've got some names of some animals. I seem to have some information about the genus and the order. I have the vor, so this refers to a carnivore, an omnivore, or an herbivore. Additional information about conservation. I'm not sure just looking at it what that is at this moment. And then some information about sleeping, about brain weight, and about body weight. And there's also some missing data here. I can see all that just from looking at the beginning of the data set. Similarly, I can look at the end of the data set. It looks similar. You can see there's additional animals here. If I really want to know what's going on in this data set, I should look at the help page. So I'm just pointing out to you as a reminder that you can do that. This is a list of all of the variables in the data set, and here there's not much of a description, but there's something short. It says that some of this information was added from Wikipedia. It looks like there's not much more available in terms of a code book than is right here. The variables that we're going to focus on here are sleep total, so how many hours of sleep does each animal get. We're going to look at vor, so is it a carnivore, an omnivore, or an herbivore. And we're also going to look at body weight and awake, how much time is spent awake. Those are the variables that I'm going to focus on just for the purpose of this illustration. I can summarize the whole data set and see these, and of course the character variables, such as the name of the animal, aren't summarized, but the numeric variables are summarized here. So I can see, for example, that in this data set, the median total amount of sleep is 10.10. I'm going to do something I usually don't like to do in my own data analysis, and that's attach the data set. That means that I'll be able to access the variables without first typing in mSleep $, and I'm going to do that just for ease since I'm focusing on only this one data set throughout this part of the tutorial. First thing I'm going to do is look at a plot of body weight and sleep total. For most of this code file, I'm going to be considering sleep total the outcome variable, and I'm going to try to predict it using various predictors. So if I make a scatter plot of body weight and sleep total, looks like this, and you can see that perhaps some transformations would be helpful here, which isn't surprising since these are measurements that have to be positive. We see that we have a lot of animals with very low body weights. So I'm going to try some logging. I might log sleep total. That looks perhaps better, not much better, and then I'm going to try logging both, and that looks much better. In fact, this looks like something I might want to fit a line to, which is indeed what I plan to do. I'm going to make this plot one more time to show another variable, this vor variable, and I'm not going to add in a legend yet, but I just want you to see that now I have displayed the relationship between log body weight and log sleep total, as well as vor, because each point is now colored according to which type of vor it is. And if I were to add in a legend, then this would be a plot that was showing the relationship between two different predictive variables in the outcome, even though it's just two-dimensional. So it's nice to remember that color is an additional dimension. Here I'm just going to create new variables equal to log body weight and log sleep total so that I can access those easily. The other thing I need to do is make vor a factor. Because if you remember, when we summarized vor, along with some of these other names, etc., of the animals, it wasn't summarized here. In other words, all it's telling me is the length and the fact that it's a character variable, and character variables aren't summarized. But I know that var takes on particular values. So for example, I know that I should be able to do this, and it is indeed true that it takes on only a certain number of particular values, but because it's currently stored as a character variable instead of a factor variable, I'm not able to do things like run regressions on it. So I'm going to turn var into a factor. Now that it's a factor, I can look at the relationship between log sleep and var, using var as the predictor. And here we go. So we've got carnivores, herbivores, insectivores, and omnivores. And the y-axis is not labeled, but the log number of hours of sleep that they get. You can see there does seem to be some variation. Mostly that insectivores seem to get more sleep. So I can summarize this var variable now, and importantly I use summary here instead of table because by default the summary command will also tell you how many NAs there are. The table command won't do that. And I can see there's 7 animals for which var is NA. So this is not a video about missing data, but when you have a categorical variable with some missingness, one option that I like is to just create another category called missing. So I'm going to do that here. Because it's a factor variable, I have to add missing as one of the levels. So first I'll just say what are the different levels of var right now, and here they are. And now I'm going to reassign the levels of var to be equal to the previous levels of var concatenated together with missing. In other words, I want this to be the set of possible things that the var variable could be equal to. So I'm going to run this line. And now I haven't changed the var variable, but what I've done is increase the number of possible values that this variable can take on. And now I'm going to say var, where var was previously NA, should now be missing. And if I do that, then when I summarize it, there's no longer an NA place, but rather missing is just one of the 5 categories, which means I won't have to drop units as I continue. And now I can make a box plot of log sleep by var. And there we go. And so I can see that this is the distribution of log sleep for the animals for whom var status was missing. All that was data cleaning, just a little bit of data cleaning to get us started so that we can start modeling. The first set of models that I'm going to run, or actually one model, but as both an ANOVA and a regression, is going to be log sleep predicted by var. Before I actually run a model, let's just look at the mean of log sleep by var. I'm going to use the by command to do that. If I look at the output, what I've got is the var listed, so carnivore, herbivore, insectivore, omnivore, missing var. And for each of those, the mean log of sleep has been calculated. So ideally, if I'm going to predict log sleep using var, my prediction should be whatever this mean is. In other words, this is what I'm hoping my model will output. It is what my model will output. If a new animal shows up and I find out that animal is an herbivore, my prediction should be this value because that's all the information that I have if I'm only using var as a predictor. So again, we've already done this, but I'm going to make a box plot because if you're going to run an ANOVA or a regression, since they're the same thing, of outcome variable on a factor, box plots are one of the best ways to go. So I can see this pattern. Right, I can try to decide whether I think the constant variance assumption is true, the normality assumption. Here I'm not going to worry about either of those things too much. If this were my actual data set, I might go ahead and continue with both those assumptions made here because I know that the method of regression is fairly robust to the normality assumption. And I'm not that worried about the constant variance given the small sample size, but the point here is not to analyze this data, but to demonstrate some characteristics of regression and ANOVA. So now we're finally to the modeling. So I'm going to call this M1, it's going to be model 1, and I'm going to write AOV because it's going to be an analysis of variance. And I'm going to use the AOV function to run an ANOVA of log sleep on var. So I've done that now, and I'm going to look at the summary of that output. So what do I get? I've got my usual ANOVA table. The predictor is var. Here's the residual error. I have the degrees of freedom for each of those. I have the sums of squares associated with each of those. By default, R does not also include the totals row, but of course the sum of squared total is the sum of these two. I've got the mean squared. The F is equal to the ratio of the mean squared, and there's a p-value. So this p-value is testing the null hypothesis that the mean log sleep is the same for each var group. And what we see here is p-value of 0.14. In other words, this data is not particularly shocking if the truth is that actually all five groups, have the same mean log sleep. I'm going to make a plot of residuals versus fitted values because what this ANOVA does is it calculates the mean in each of these 5 groups and then calculates the residuals from the separate means model in order to compare them to the residuals from the equal means model. In other words, for example, this data point, the residual is how far this animal's log number of hours of sleep is from the mean for all omnivores. So I have residuals and fitted values, and I can make a plot of them, right? Just showing you that I can do that with the ANOVA. Residuals and fitted values. And I can add a horizontal line to that if I was interested in checking whether the values were equally likely to be above or below the line, right? Again, we can see that I can just spit out these fitted values. If you just look at these, you can see that these values here, 2.22, 2.36, 2.07, they're chosen from this set of numbers up here. Here's the 2.22, right? The 2.078. Because the predictions that we're making for each of these animals, the fitted values are just equal to the means from their group. Again, if an animal is an herbivore, the fitted value for that animal is the mean of the log sleep for all the other herbivores, including that one. What I'm going to do here is just make a little data set to show you a bunch of columns together. The VOR column, the log sleep column, the fitted values, and the residuals from this ANOVA so that we can look at them all together. Scrolling up to the top of this table, so you can see, for example, here's an animal that was a carnivore. Its actual log number of hours of sleep was 2.493. The fitted value was 2.22 because that's the fitted value for all the carnivores, and the difference between these two is the residual, right? So 2.49 minus 2.22 is 0.27. The residual is exactly log sleep minus fitted value by definition. So that's what these are. The fitted values are just the mean within each group. The residuals by definition are the actual outcomes minus the fitted values. I'm going to display the output from the ANOVA again. And I want to show you that we can directly use these residuals in order to recreate the values in this ANOVA table. So for example, if I take the vector of residuals and square each value in that vector and then add them all up, that's the sum of squares residuals, right? So I can do that. I have a dot 1 here just to remind us that this is the first model we're looking at. If I do that, I get 20.864, and indeed that's the same number that I have as my sum of squared residuals. So the output of this ANOVA is not magic. This is literally the sum of the square residuals. I can also get the sum of squared total. So if this were an equal means model where I was ignoring VOR, I could take log sleep minus the mean of log sleep for everybody. So this is each person's log sleep minus the overall average. I can square those and then add them all up. And if I do that, I'm going to have a sum of squared total. By definition, the sum of squared due to the model is sum of squared total minus sum of squared residuals. So if I do that and print it out, now I'm back to my 1.894, and there it is, 1.894. So you can confirm the results in this ANOVA table just based on the data itself. There's nothing mysterious here. Each of the mean squares comes from sum of squared divided by degrees of freedom, etc. So that's the ANOVA. We ran an ANOVA of the continuous outcome on this categorical variable. But what happens if I instead specify a regression model that looks at log sleep by this categorical variable, by VOR? So I'll make a plot where the x-axis is going to be VOR and the y-axis is going to be log sleep. Note that when I do that, I just get back to the same box plot because when the variable you put in the x-axis is categorical or a factor, R will just draw you a box plot instead of a scatter plot because you can't make a scatter plot with an axis that's not numeric. Now I'm going to run the regression, so it's going to be M1 because it's the same model, but .lm because I'm running it as an LM, as a linear model of log sleep on VOR. Okay. When I summarize this, the output is going to look different than the output of the ANOVA, even though it's the same model, because by default the regression presents different numbers as part of a summary of the model fit. Let's go look at this. So what's in here? The first thing that comes out of the regression output is just a repeat of what you put in case you forgot. So that's helpful. The next thing is the summary of the residuals. So let me skip down to this. I have in the code down here, actually for the ANOVA, but it works for the LM as well. Here, I'll add it. Why don't I add it right where we are? So if I look at the residuals and I summarize the residuals, you can see that this output right here matches exactly what comes out. There's different rounding, but what comes out of the summary of the regression itself. So that's just literally a summary of the residuals. Then I have my table of coefficients. Here are my estimated coefficients, their standard errors. The t-values by definition are the estimates divided by the standard errors, and then a p-value for each of those. What are these p-values showing? Well, as in any multiple regression, each p-value is comparing the actual model I ran to what that model would be like without just one row. So for example, this 0.807 says that under the null hypothesis that you don't need the indicator for VOR being missing, this data would not be surprising, right? So this model that we have here with indicators for herbivore, indicator for insectivore, indicator for omnivore, indicator for missing VOR, is not any better than a model that just has the first three. That's what this 0.807 means, that this term the data doesn't contradict the assumption that we don't need that particular row. Okay, so we have those. We can again make fitted value and residual plots, residuals versus fitted value. So I'm going to make that plot. And although you may not recall, that is exactly the same plot we saw before. And if you're following along by downloading the code, you can check that. That's exactly the same. But let's start to check it. So here I'm going to put together in a matrix the fitted values from the ANOVA and the fitted values from the linear model. And what you can see is that for each row, those are exactly the same number, because what each of these models is doing is fitting the mean within a group as the predicted value, as the fitted value. So if you are a carnivore, then regardless of whether I call it an ANOVA or a regression, the mean for somebody like you is the mean in your group, in your VOR group. Similarly, I could do cbind to make a similar matrix showing you the residuals from the ANOVA and the residuals from the regression, but that would be boring because it's exactly the same idea that I just showed. Instead, I'm going to show you there's a function in R called identical, and I can ask if these two vectors are identical, and lo and behold, they are. In other words, both the ANOVA specification and the linear model specification are just splitting the sleep totals into groups based on VOR, and the predicted values are exactly the mean in each of the VOR groups. And the residuals are just the actual log sleeps minus the fitted values of log sleeps. Similarly, I can get the coefficients out of either of these models. Even though the ANOVA didn't show me the estimates of the betas, the coefficients, and the linear model output did, right? So this says that my model is 2.22 minus 0.14 times herbivore plus 0.41 times insectivore, etc. These estimates didn't come out as part of the ANOVA output by default. But if I either type m1.lm and then give me the coefficients, right? If I do that, this is the linear model output, it gives me just the vector of these coefficients. I could do the same thing with m1.aov since it's the same model, right? And that's exactly the same vector of coefficients. So even though the ANOVA didn't explicitly, as part of its default output, give me the coefficient estimates, that's part of what's going on. That's the same set of coefficients that are used. Now let's try to understand that better. I'm going to again look at log sleep by VOR. So the carnivores are the default, the omitted value here. In other words, of this categorical variable that has 5 levels, the 4 levels that are listed as indicators in the model are all of them except for carnivore. R by default will always choose the one that's first in alphabetical order as the baseline. Okay, that's why the intercept is 2.22. It's equal to the mean for the carnivores. If you're not an herbivore, and you're not an insectivore, and you're not an omnivore, and your VOR is not missing, then you must be a carnivore. All these terms will be equal to 0, and you'll be left with the intercept, which is 2.22. However, if you're an herbivore, then you should have a 1 for your herbivore indicator and 0 for all the other indicators. And so our estimate of your log sleep should be 2.22 minus 1 times this quantity. In other words, it should be equal to 2.08. So this specification, these set of coefficients, is just another way to say that we're going to use as your predicted value whatever the mean is in your own group. And that's true regardless of whether we call this via ANOVA or via a regression. I want to look at these two sets of outputs next to each other again. Let me do this. So I'm going to summarize the ANOVA. I want to point out that if I, instead of saying summary m1.lm, say ANOVA m1.lm, so in other words, if I use the ANOVA function and give it the output from the regression, I have to hide the whole thing, it gives me back exactly the same table. Okay? So again, this is the summary of the ANOVA. This is ANOVA parentheses output from the linear model. These are identical. Right? So what I'm showing you is that you can run it as an ANOVA or you can run it as a linear model, but either way, the coefficients are being estimated and the sum of squares ANOVA table is being calculated. It's the difference is the default in what's usually shown. I also want to, as we're looking at this one more time, have it print out the usual summary of the linear model that is here. So I want to compare it again to the ANOVA output. In particular, I want you to see that this ANOVA right here, which is testing the null hypothesis the means are the same in each group, is the F test that's summarized on the bottom row of the regression. So everything that's relevant about the ANOVA table actually does come out in this case as part of the regression output. We've got our F statistic 1.77 on 4 and 8 degrees of freedom. Here's degrees of freedom. We've got our p-value 0.1432. There it is, right? The bottom row of the regression, by default, will compare the model you specified to the equal means model. And that's, in this case, with only one predictor. That's the same as saying, are the means the same in each group? That's the equal means model compared to this alternate model, the separate means model, where there's a different mean in each group. So again, the very bottom row of the regression output gives the same thing, in this case, that you'd get if you just did the ANOVA, because this is a test for whether this model is any better than an equal means model. And that's exactly what the ANOVA was asking as well. So in this case, there is nothing new to be learned, from running both the ANOVA, showing both the ANOVA output and the regression output, because the ANOVA output is actually summarized as part of the regression output. In fact, there's nothing mysterious about the values in this regression output. So we said that this is just a repeat of what went in. This is the summary of the residuals. We talked about the coefficients. We talked just now about this row on the bottom. What about these other two rows? There's only 2 more rows in this regression output that could possibly be mysterious. So first I want to point out that the residual standard error is the square root of sum of squared residuals over degrees of freedom. So let's think about the ANOVA table again. Here's our sum of squared residuals. Here's our degrees of freedom. If we take sum of squared residuals divided by degrees of freedom, by definition we get the mean square error. Okay, so here I'm going to calculate that. Earlier I calculated sum of squared residuals. Now I'm going to divide that by 78, that's the appropriate degrees of freedom, and get the mean square error. And if I were to look at that, I can see that's 0.267. Lo and behold, that's the same mean square error shown in the ANOVA table. And if I were to take the square root of that, 0.517, that's the number shown here. That's the residual standard error. So these two different sets of outputs are just choosing different ways to show you the amount of error there is, either by the square root of the sum of squared residuals over degrees of freedom, or by just showing you degrees of freedom, sum of squared residuals, and the mean square. So now this row is not mysterious anymore. This is the same thing that's shown in the ANOVA table. What about r squared? Multiple r squared just means r squared. There's nothing, that word multiple contains no information. So, but one of the definitions of r squared is that it's the sum of squares due to the model divided by the sum of squared total. And we calculated these two quantities previously using the ANOVA output, using the residuals from the ANOVA, in fact. So if I take the ratio of those two, I get 0.083. That is the same as the multiple r squared. So this multiple r squared shown here is literally sum of squares due to the model divided by sum of squared total. Another way to say the same thing is it's 1 minus proportion of the total sum of squares due to the residuals. So that's exactly the same number. And we can confirm the adjusted r squared as well using the formula for that. So it's 1 minus sum of squared residuals divided by its degrees of freedom over sum of squared total divided by its degrees of freedom. And now I can confirm the adjusted r squared as well. There's this number and this number. So there's nothing mysterious anymore in the regression output. And any of the values here we can calculate looking at the residuals that pop out when I run it either as an ANOVA or as a linear model, because those are the same thing. Next, I'm going to run a model that looks at log sleep by a different predictor, in particular log weight. So let's look again at the plot of log weight and log sleep. Here we go. So we've got this negative correlation. I can try to make a box plot of log sleep by log weight. That's just going to look silly, just to point that out, because log weight is a continuous variable. What it's trying to do is, for each different value of log weight, show a box plot of log sleep, but every animal has a different value of log weight, so that's not working particularly well. These are all lots of tiny box plots, just to show you that doesn't always work. However, if I round log weight and make a table of it, then you can see if we round weight, well, there's 2 animals whose log weight is rounded to -5, 5 animals whose log weight is rounded to -4. Now we actually have some groups, and so now I would be able to make a box plot if I wanted to look at the distribution of log sleep by a rounded value of log weight. This shows you the same sort of distribution. I like this plot in addition to the scatter plot because it emphasizes the idea of what a regression is doing. Even for a continuous variable, the regression says fixing a particular value of the predictor, what's the distribution of the outcomes. So you can think of a regression in the same way we thought of f-tests for ANOVAs, where the x variable, the predictor variable, is just breaking down the data into groups. But let's go back to this plot because that's the one we're actually going to study. This time I'm going to start by running the regression because that's the thing that comes naturally when we're thinking about a continuous predictor. So I'm going to go ahead and run that, and then I'm going to summarize it. And of course what I'm going to get is the type of output I expect to see from a linear model. So I have an intercept and a slope, right? And p-values for each of those. I also have an f-test. So that's interesting. We'll come back to that. I've got my r squared, and I've got my residual standard error. I can make a plot of residual versus fitted values just as I could before. Right there it shows up. We can decide whether we like that plot, but right now the point is that we can make it. Okay. But I'm going to go back to the original plot and add the regression line to it. So you can see that's a reasonable line, and it has the intercept and slope that are specified right here. So this seems like a pretty standard thing to do for a continuous data set like this one. Now I'm going to do the thing that may seem counterintuitive if you're used to dealing with continuous predictors. I'm going to run an ANOVA instead of an LM, a linear model log sleep on log weight. So I'm going to run that and look at the output for it. And of course the output now will be summarized as an ANOVA because that's the default for an ANOVA. Okay, so what is this? So let's look at this output, and I'm going to just, so we can compare it again, summarize the regression output. Okay. We've got these 2. The first thing I want you to note is that these p-values are identical. So the p-value that came out of the ANOVA for log weight is identical to the p-value that came out of the came out of the regression for log weight. What is the ANOVA doing? What is it showing us? Well, it's showing us that sum of square residuals. It's showing us the sum of squares that seem to be due to the model, so total sum of squares minus sum of square residuals. And it's comparing those to tell us how likely the data would be under the null hypothesis that the equal means is true, as opposed to the linear model. The way to tell that the variable that was used here as a predictor is continuous is its degrees of freedom here is equal to 1, as opposed to a larger number reflecting the number of categories, -1. So when you look at the ANOVA output, what this is telling us is that this data would be really surprising, the p-value is essentially 0, if the truth is that no matter what the log weight is, the log sleep would be the same. This data would be shocking if the truth is that log weight is not actually a predictor. Rather, the regression model seems more compelling. That's exactly the same question that's being addressed by the output from the regression. This right here, we usually talk about, the one I've highlighted, we usually talk about it as a test for the null hypothesis that the coefficient for log weight is equal to 0. But that's the same as saying that under the null hypothesis that an equal means model is correct, this data would be surprising. If the coefficient for log weight is equal to 0, then that means the equal means model must be true. In other words, the slope must be 0. Just one horizontal line must be the right line. And this p-value is telling us this data would be really shocking if the right model is just one straight line, one equal means model. So these 2 sets of output are answering exactly the same question. That's why it's the same test. The p-values are identical, and in fact, if I were to take the square of the t-statistic shown here, I get 54.58, and in fact, that's the F value that's right here. So it's literally the same test. The t squared is the F. The p-values are exactly the same. In the case with one continuous predictor, the ANOVA p-value is exactly the same as the p-value for the t-test for that predictor from the regression output. And so we can also see then this is the same f-test, the same results of the ANOVA, a typical ANOVA format, shown at the bottom of the regression output, right? This too is the same. It's different rounding, but this too is the same p-value. Here's a 54.58. That's this t statistic squared. Remember that the f-test shown on the bottom of the regression output is always going to be comparing the model you ran to an equal means model. And in the case of only one predictor, that's the same question being asked by this line here. It's comparing the model I actually ran to a model without this one predictor, so an equal means model. So this line is a summary of exactly this f-test, which is exactly identical to this t-test that we have right here. I can go through the same process I went through before if I like to verify the sum of squared residual and the sum of squared model. So if I take the residuals from the linear model, square them, add them up, I get the sum of squared residual that is equivalent to what I saw in the ANOVA table. And if I take sum of squared total minus sum of squared residual, I get sum of squared model. My sum of squared model is also identical to what I saw in that table. And I want to show you just again that if I ask either of the sets of model output for the coefficients, I get the coefficient either way.